Hello pre-calc students, I hope you're all well. This supplemental video for the chapter which introduces or reintroduces to us exponential functions is intended to just briefly summarize what we would have done if we were in class together today. All right, this slide that you see in front of you right now is intended to be a real-world example which demonstrates a skill that was taught in the other video for this lesson. So in that video, you were given 2 points on an xy plane, and you were tasked with finding an exponential function that passes through those 2 points. And we're seeing that that technique can be applied to studying populations, such as world population. We see these 2 actual data points. Back in 1988, the world population was estimated to be about 5 billion, and then it increased to 7 billion around 2012. And notice how the axes are defined here, where the horizontal axis, which we usually have called the x-axis, is defined to be the number of years since 1980. And therefore, the years 1988 and 2012 are represented by t equals 8 and t equals 32, respectively. And we see that we're going to measure the population in billions. So 5 and 7 represent world populations of 5 and 7 billion. And if we're being good math students, we should certainly make sure our axes are clearly defined. So P of t, the population in billions of people on the vertical axis, and t, time in years after 1980 on the horizontal axis. If we use that technique that was demonstrated in the other video for this lesson, we might ask the question, come up with a population model, an exponential population model. And again, using that technique from the other video, you would come up with this equation. Presumably, you'll often just use the decimal approximations, making sure to stow your values as emphasized in the other video. But notice it can also be written in its exact form, and depending on the situation, you may or may not decide how to represent it based on the situation at hand. But for our purposes in this chapter, I'll generally be okay with either form, although I'll be sure to specify if we need it to be one form or the other. We could also ask the question, according to this model, what would the world population be in the year 2020? I made this slide some years ago when we still would only have been speculating what the population would be in 2020. According to that model, since 2020 is 40 years after 1980, if I plugged t equals 40 into that equation, that model would have told us that the population in 2020 would be 7.831 billion people. If I go to the World Population Clock webpage, we see that according to their model, it's about 7.8 billion people. Now, keep in mind that our model, as well as the model on this website, are just models. They are not intended to be perfect, despite the fact that this webpage kind of implies that it's more precise than it could possibly be down to the person. We should know these are just models, and nobody knows for sure at any given time what the world population is. Switching to the next slide, this is a graph from that same website which shows a graphical form of world population over the centuries. And just visually, it sure looks like an exponential model. And populations are often represented by exponential models, but one should keep in mind other factors as well. And if you have reason to believe that the population may start to deviate from an exponential model, one should take that in mind. For example, if I go ahead and uncover some of the more recent years, we see just visually, it looks like the Earth is starting to, or at least if we make some assumptions, it looks like the population may be leveling out. And as far as what it will level out to, that's a whole nother discussion, but one would have to keep that in mind when trying to employ that population model from the previous slide. All right, here's a quick example that is relevant to your homework, supposed to help you out with the homework if it wasn't already obvious. I'm not going to do every single one of these exercises. I'll just do a few that kind of get the point across. You're being tasked to identify which of these are exponential models, exponential functions. So for starters, let's just real quickly review what is an exponential function. In short, it is any function that may be expressed in the form y equals a times b to the x power, where a and b are both constants. So let's go ahead and start with exercise A. Sometimes students get a little thrown off because they see the b to the x, but they wonder where is a in this equation. Well, we could certainly think of that as 1 times 3 to the x power, right? So we're going to say, yes, this is an exponential function. And in this case, the initial value, represented by a, was 1, and the base, represented by b, is 3. All right, simple enough start. Let's look at B, exercise B. If you're careless, at first glance, that looks like it roughly fits the form y equals a times b to the x, but you look a little more closely and you notice that the variable x, in this case, is in the base, whereas for an exponential function, the variable is supposed to be up there in the exponent. So as far as vocabulary goes, I would call this a power function, not an exponential function. I'm not going to belabor that use of the term power function at this point. We'll simply say this is not exponential. And since it is not exponential, I don't need to answer that question about the initial base, or the initial value and the base, because those questions don't apply. I hope you can look at some of the other ones here and kind of see how this goes. I'm going to jump ahead to G, which is definitely a trickier one. So that's the one that we would spend some time on in class. It'd probably take us about 5 minutes to get through it, but I'm going to do the super rushed version of it here. At first glance, that looks like it may not quite fit the form of a times b to the x, but as long as it can be written in that form, then we'll call it exponential. And we're going to find that, yes, this can be written in that form. So we're going to need to know our exponential properties, which you were reminded of in the other video. So let's use some of those properties, and let's rewrite this function. S of theta equals 5 times 4 to the 2 minus theta. Remember, that can be broken up in a couple different ways. You may decide to write that as 4 to the 2 divided by, oops, pardon me, 4 to the theta. That is totally valid. However, to see if we can make it in the form of a times b to the x, rather than using that quotient property of exponents, I'm going to use the product property of exponents, which you should also be familiar with. That's the one that says I can think of that as 4 to the 2 power times 4 to the negative theta power. Recalling that if we just add those two exponents, 2 and negative theta, that gives us the exponent we had in the original problem. All right, let's simplify. 5 times 4 squared, that's 5 times 16, so that is 80. 4 to the negative theta, let me use another exponential property that says I can think of that as 4 to the negative 1 and then to the theta power. Remember, in that situation, when you have exponents on the inside and the outside of parentheses like that, that's where you multiply them, and that's what would give you negative theta here. I'm doing this because notice our definition of exponential properties require that you have an x, of exponential functions I should say, that you have an x there and only an x, no other clutter up there in the exponential position, no negative signs or coefficients or things being added or subtracted. So I know that 4 to the negative 1 power is 1/4. So I can say that that is 80 times 1/4 to the theta power. And now I have that in the form of a times b to the x. So I will say, yes, this is exponential. And a equals 80, b equals 1/4. And due to the fact that that 1/4 is less than 1 but greater than 0, that tells us that this would be exponential decay. If you were to graph it on your calculator, or by hand, the graph would be decreasing, and the a equals 80 tells us that our initial value there is at 80. Okay, very quickly, I'm going to address the last one, h, and say that is not quite exponential, although I think it's common for many people, including myself, to kind of sloppily call that exponential at times. But by the letter of the law, because of that vertical translation there, this graph is not asymptotic to the horizontal axis, and therefore technically it's not exponential. Exponential needs to fit the form a times b to the x. There's not really an allowance for a vertical translation at the end. So, last one, not exponential. All right, for our next example, I'm going to just very quickly flash this worked out example on the screen. Again, if we were in class, we would go over it and have a little more discussion, but I'm hoping that if you pause this slide and just study it for a bit, you'll affirm that you know how to do this. If you're simply being asked to evaluate certain values of an exponential function, as you will on the homework, you'll have to use a few of your exponential properties as demonstrated here. All right, last example for the supplemental video. Oh, by the way, if you're interested, if you're curious, in class we would have gone over this slide and found out that 6 of those could be using exponential and, in a couple cases, logarithmic properties. You could find out that 6 of those are actually the same function and 2 of them are not. But we'll save details on that for another day. All right, last example here. This one is intended to be quite quick, and when I've had it on tests, students often get it, but they often use a technique that is similar to one from the other video in this chapter, yet that's a little bit overkill. So here are 2 functions, g of x, they're the x and y values, and also h of x. And what I've seen students do in the past is not entirely bad. I've seen students say, oh, I only need 2 points to determine an exponential function. Here I've got more than 2 points in both cases. So for example, you could take this point on the g of x and this point on the g of x. And thinking back to the other skill, if you plotted those 2 points, again, we really only need 2 points to find an exponential function. So students would proceed that way. However, in this case, we've got more than 2 points, and especially valuable to us will be that 0 point, that point where x equals 0. It turns out that when you know the the y-intercept, 0, 4, when you know that the y-intercept, as I'm showing here, that is always going to be your a value if that has not already been made clear to you. That is what we call our initial value, your a value. So when you're writing an exponential function in the form of a times b to the x, we know that the a value will be 4 right off the bat. As far as the b value goes, as long as the function, or as long as this table is incrementing by 1, so 0 to 1, 1 to 2, and so on, the b value is what you could think of as the multiplier when you go from one step to the next. So from 4 to 12 in the y column, I'm multiplying by 3. And we see that that is the same multiplier for the other values as well. 12 times 3 gives us 36. We see that if I back up on the table, times 3, times 3. So if that number varied at all, if for instance we had a 3 here but a 2 here, that would be a sign that this is not an exponential function. But in this case, because we are dealing with an exponential function and that value is constant, we would say that there's our initial value, y equals initial value 4 times this multiplier, this base, 3 to the x. And I guess since that function was given a name, I should use it. That was g of x. Similar reasoning for the other function, h of x. I'll do that one a little more quickly. Again, the initial value that aligns with x equals 0 is 8. That means that h of x equals 8 times some base raised to the x power. Let's see what that base is. Make sure that you focus on what you're multiplying and not dividing. It's very easy to go from 8 to 2 and think, oh, my base is 4. But no, it's not. I'm not multiplying by 4. I am dividing by 4, which is the same as multiplying by 1/4. Again, just affirming that that is the same multiplier in the other instances. 1/4, 1/4 in all cases. That affirms for us that that is our base. So h of x is 8 times 1/4 to the x. To be clear, if you use that other technique shared in the other video, if you just picked 2 points from the table and use those 2 points using the technique from the other video, you would have gotten the same answer. You would have gotten a right answer, but this is just a quicker way when you're given more information. All right, hope that's clear. Please attend office hours if you have any questions on any of this.